Hello and welcome. Today I'm going to talk to you about visual group theory. My name is Jeff Washburn, and this is a project that I'm doing for my data science class, 7335 Machine Learning 2. So let's get started. What is visual group theory? So visual group theory is not about numbers, but more about patterns and symmetry. And things where you'd see this in would be like puzzles, art, music, cryptography, all throughout mathematics. There's four parts to group theory, or we'll give it like an informal definition. So, four rules. There's a predefined list of actions that never change. Every action is reversible. Every action is deterministic. And then any sequence of consecutive actions is also an action. So, a group is a set of actions satisfying rules 1 to 4. And a good example of this that we might be familiar with would be the Rubik's Cube. So there's two sequences of moves that would be indistinguishable. So let's just say those moves are the same. So rotating the face by 90 degrees is the same as rotating the face, 5 degrees, you end up back where you started. There's an infinite amount of possibilities on the Rubik's Cube, but there's truly distinct moves that can be done. So if you think of a map of the solved state, then there's only so many moves that you can do without repeating and so forth. So in the end, there's 4.3 times 10 to the 19th moves generated by just 6 moves, and those are with the clockwise twist of the six faces. So let's go over a few of the concepts of what a group is. So a group is a set of actions that can be performed. So the Rubik's Cube itself would be the group, right? And those are, again, the actions that you can take, the reversible, deterministic, and the consecutive set of actions is itself an action. So a generating set is a sub-collection of actions that produce all the actions in the group. And then generators are the individual actions in the generating set. So again, the Rubik's Cube, so many combinations and actions that can be taken, infinite number. But if you look at the distinct set, again, there's 4.3 times 10 to the 19 actions on the generating set of size 6. So a few other concepts that go along with visual group theory are called Cayley graphs, and it's just simply a mapping. So it's named after the British mathematician Arthur Cayley. So it consists of nodes that are connected by arrows, and in this case here we'll use like blue arrows represent horizontal moves, and the red arrows represent the vertical moves down, right? So you have on the arrows the generating G is it's basically from X to Y means that the node Y is a result of applying action G to the node. And if it's reversible, you have the double arrows that it's showing there. What I've found in doing the research on this is a lot of people will take away the double arrows, just represent that it is reversible. So if there's an arrow indication, like on the first one on G from X to Y, that just means you can only go from X to Y, but you can't go back. Whereas on A to B, you can go A to B and then back from B to A, so it's reversible. So what this represents in getting into it is, let's use a triangle, for example, right? And so there's 6 actions that we can take, right? And so our starting point, if you look at our starting point here, which is the kind of the darker gray, E is identity. This is kind of our starting point. This is the do nothing state. And then if you go to R, this is the one rotation. Notice the numbers, if you rotate the 3 comes to the top. R squared means you rotate yet again, and then the 2 moves to the top. And then an F is a flip. So we'll do the red arrows are rotations and Fs are flips of the triangle. So an R rotation would be 120-degree rotation, and then R squared would be 240. And then if you do R cubed, that's the same as going back to E. So what we're showing here then is the generating set of a D3. We have 2 actions we can take, R and F, so a rotate and a flip. Then the relations are the multiple paths that lead to the same node. For example, like I said, R3. So if I start at E, R3 here is R1, R2, and R3 gets me back to E. R1 is equal to R2, meaning I can go to R1 and then I can get back to through R2 backwards. So R1, R2 gets me back to R. And so RF, so if I go R and then F, right? That's the same as going F and then R1, R2, R squared. That gets me back to the same triangle. So we'll get into this concept called non-abelian. So non-abelian means order matters. So in this case here with the triangle, RF doesn't equal FR, meaning if I go RF, that's not the same as going FR. That gets me to a different location, right? Now the math and the multiplication, there's math behind this, multiplication tables. And basically here, well, E is our identity. This is our starting point. H is our horizontal, and V is our vertical, and R would be a rotation. So you have your rows in your columns, and that just represents the states that you're in. So for example, if I go E to H, I end up at H. So E to H. So here's E, H, I end up at H. If I do a V, let's go VH, V times H, right? It says I'll end up at an R. So if I do a V, so a vertical, and then a horizontal, I end up at R. So the multiplication tables, a lot of color is put behind this to give some indication where you can start to see patterns. And it starts to be relevant like on these abelian groups where the across the diagonal, if you were to flip this on itself across the diagonal, the colors would be the same. And we'll go into some groups and why that's important. On the next slide here, this is an example of the multiplication table for the D. I showed it earlier, right, where we have the rotations and the flips. So R3 is equal to the identity, meaning if I go R3, so R1, 2, and 3, I end up at the identity. So here, if I can go, and you can look at any of the math factors. So let's say R squared to F. So R squared, I start at E, R squared, R1, R2, and then at F, I end up at R2F. So if I look at E, and then I do R2F. So here's my rotation, here's my RF, I end up at R2F. So you can use these tables to get an idea of what the pattern is going to look like. Now we'll go into the different kinds of groups that show up in group theory. There's 5 different groups. First one is the cyclic groups. This is similar to like pinwheels, propellers. They look the same from any viewpoint if you're ignoring the colors. So all positions can be seen by doing a 1/8 turn. This occupies the same space. So notice if I were to turn this pinwheel an eighth of a turn, it would always look the same, just the color would be different. So the pinwheel symmetry forms a cycle. So 8 symmetries is called a cyclic group. So here's an example of what it's like, with a pinwheel. And then from a Cayley graph, this is what it would look like. So in R3, here's my starting point, R1, R2, and R3. Now we get into dihedral groups. So this is a progression of just taking a triangle, right? And the triangle at the, say, the top left, we got the red dot. I can rotate this. And so if I rotate it, notice red dot, but I can also do a horizontal flip. So the blue dot represents the horizontal flip, whereas the green represents the rotation. If I were to put that into a Cayley graph, then you'll notice that in the middle diagram here, it's similar to what we're talking about before with the D3 with the flips and the rotation. So the green arrows represent 120-degree rotation. Blue lines represent horizontal flip actions. So rearranging the Cayley diagram looks like the image on the right. And then a 2-cycle structure, the inner structure rotates opposite direction of the outer. So remember, as you rotate in one direction, then when you flip it, you're actually going the other direction. So there's alternating groups. So this is a tetrahedron. So think of a tetrahedron, you got a triangle at the bottom and a pyramid basically, right? Now there's 12 different positions. That's what we're showing at the top left. Kind of plays tricks on your eyes here. So the middle shows each rotation and each position. So if you think of the middle diagram here, This is like the top of the pyramid, but in each position you can rotate it, right? Or flip it. So this is showing the different positions that it can be in. And then the right diagram removes the tetrahedron and just shows the rotations at each point. So this gets us closer to the Cayley diagram. The third type of group that you can do in group theory is symmetric groups. So here's an example of a icosahedron. And then the one that I wanted to touch on a little bit more detail are the abelian groups. So the blue arrows all follow in parallel left to right, then wrap around to the left again. The red arrows follow parallel top to bottom, and then they wrap around to the top again, right? So the final diagram on the right-hand side, it looks like a grid, right? And then and it's not tangled. So therefore, an R, a rotation, right? A red uh, times a blue, I'll end up here is the same as going blue times a red, right? And so it's always going to get you back in the same. So in this case, order doesn't matter. So you can go at any order. There's from a I guess presentation of 1D, 2D, and 3D, it looks like, it looks like the grid. So no matter where you start in the group following R, then B gets to the same destination as B, then R. So this is what causes a diagram to be full of squares. Groups with this commutative property, so this is called abelian groups. So hopefully, this was an interesting topic for me to study. It definitely a lot there. I got to give credit here. I mean, a lot of these diagrams and so forth that I'm using. Nathan Carter, Visual Group Theory, has a book out there that is good. What I found the most helpful was this course that Matthew Macaulay did called Modern Algebra. It's out of Clemson. He had a wealth of videos. It goes into tremendous detail. I'll be honest with you, I'm just scratching the surface on this. There's a lot to it. And I think it was an interesting topic to study. I appreciate the chance to do this. So I'll stop there. Thank you all for your time. I appreciate it.